Our esteemed speaker this evening has over 20 years of industry experience. Please welcome the CEO and co-founder of SQream, Arnon.
Hi everyone, thank you for dropping by. I have a flight to catch, so I will have to scram later on. But I wanted to share with you why we started this GPU database adventure, and later on our team will show you some stuff we do with the product and a little bit about GPU database. So we have here Joel, it's right there, Matt, Crystal, and Arnon, and I'm more than happy to answer any of your questions. Yeah, great team. So a few years back, me and another guy, we were looking at Gpgpu algorithms, playing a little bit with algo trading and other stuff that was done back in the days. And I thought, and he thought, it's going to be cool to have a Cartesian product running on a GPU on a dataset that is bigger than the memory stack of the GPU. This is how we started. We thought it was going to be cool to do a join on a large dataset bigger than the memory of the Tesla that we used at the time, and that was it. So the idea is that CPUs are progressing linearly in the last few years. I don't know if you noticed. And GPUs have been known to be very good with game video rendering, game rendering, and some Gpgpu applications. But doing a simple join on a GPU, I can tell you that not even one investor wanted to invest in this startup in these days. Everybody told us we are crazy. Funny thing, IBM did a due diligence on us. That was in 2010, and I met this professor that was part of the team who wrote the chess algorithms of Deep Talk. I don't know if you guys remember. It was groundbreaking at the time. And he looks at me, and I'm telling him what I want to do. And he tells me, you know that my thesis is about that it's impossible to do Cartesian product with multi-core chips, GPU. So we didn't pass the due diligence with this guy. So a few years later, GPU processing is more than the standard data crunching techniques, and you see a lot of companies coming up. You mentioned a few of them. There are a few more coming with even newer chips, and we're going to show you a little bit out of that. The company was founded in Tel Aviv, in Israel. We have sales and operations in Asia, Asia Pacific, Europe, and we decided that our headquarters was going to be in New York. And usually for Israeli companies, 95% of the enterprise companies are going to the Silicon Valley, and we thought, you know, it's cooler. Cool is a key thing in the way we decide how to do stuff. And New York is cooler. So we started at, I don't know if you heard the name Silverstein, Silvertech Ventures. So Silverstein, the owners of the World Trade Center complex, they have a special accelerator for companies that are doing groundbreaking technologies. And we sit at the World Trade Center with nice views of the Oculus, the pools, and the Freedom Tower. So we may have a meetup there as well. It's cool to be there. And this is our headquarters and the spirit of our operation. So I'm more than happy to share our adventure with you guys. And just before I move over to Arnon, to show you some stuff about GPU database and some things we do. We are in the business of very large data sets, right? So for us, data sets that are below what used to be a very large data set, but today not so much, databases that are below 4 terabytes of raw data. They are interesting for whoever works with them, but this is not our business. We started trying to break the barrier of the memory of the GPU, and this is what we do. We are working on datasets that are growing, and they are much more than 8 terabytes. We have clients with 1 petabyte doing genome analysis, and we have clients between 300 and 30 terabytes and 300 terabytes. And this is where we are looking for partnerships and for applications that we can collaborate with. Right, so thank you very much for coming over. I know I was much more boring than the swag, but anyway, Arnon, thank you.
I'm sorry you have to hear me instead of him. He's a little bit more entertaining. The meetup title is a bit of a mouthful, so we have a short acronym. It's much easier to say. So I will say this ahead of time. We have a bunch of people here, Joel, Crystal, Matt, and we will offer free consultation to anyone who finds this interesting. So if you think this is interesting, this is for you, then come talk to us and we will offer free consultation and we will help you identify if this is right for you. So I originally had Ami's slides, but I've changed it to mine. So I'm from Israel. I've been at SQream for 4 years. I originally started as part of the dev team. I worked on the SQL compiler. And I tweet about animals a lot, if that's your thing. Animal GIFs, dogs, that is my thing. I'm also a huge airplane nerd, so I might tweet about that as well. Just, you know, fair warning if you're going to follow me. A few months ago, The Economist came out with this article. I just took the image from there because I think that's, everyone likes the images, right? No one cares about the text. And they said Moore's law is ending. And you can see, really, the clock speed. And the clock speed around 2005 sort of peaked. And I'm sure you all remember you would have these 400 megahertz CPUs, and then 500, 600, 800, 1,000, 1,500. And that sort of stopped around 2005. You would get 3 gigahertz, and it doesn't really go above that. I mean, some situations, if you like overclocking, not recommended for servers, by the way. So CPUs have sort of peaked, but Moore's law is not ending because we're still adding more transistors, right? And that's what the law is about. It's talking about more transistors. But instead of making the clock speed faster, we're adding more cores. And Intel sort of started that with the Core 2 Duo, where you would have 2 cores in the same die. And I think in most of your phones, if you all have iPhones, you probably have like 6 cores. Some have 8. But in essence, this is a quote from a Microsoft guy, and he said, the consensus was that if we could keep adding cores and we could reach 1,000 core CPUs, we would be just fine. Everything would be fine, sorry. Didn't memorize that right. But it turns out that's really, really hard. And he's a chip expert, so he should know what he's talking about, right? So the thing is, when you add more cores, he's saying, let's just make things parallel, right? So you have each core doing their own thing. And that works well in some scenarios, but it's not true for everything. Not everything can be parallelized. And there's this thing, they call it embarrassingly parallel. Embarrassingly parallel means it's very easy to do, it sort of begs that you make it parallel. And that's not true for everything. And that's not true for data processing, for databases. So let's talk about data for a second. Because unlike CPUs, which have sort of peaked, data has not. It's still growing, and it's growing exponentially. So what was the norm in 2010, which was, let's say, 10 terabytes, that's no longer the norm. We're talking much more data. And this is a problem when you want to analyze it, because we're in the petabyte age. And petabyte age means lots of data. So it's no longer, 1.5 terabytes for a company. A small company might have tens to hundreds of terabytes. And we're in talks with companies like that, and we're saying, we can't afford these really, really expensive solutions. We know about all these, but we can't afford them. And you might not be Google, right, with 15 exabytes. But what if you could get Google's type of solution, right, for a lot less? You don't want to pay Google's. You don't have pockets as deep as Google, I hope. If you do, we should talk. But it's a problem, right? It's a problem for a lot of companies. And NSA estimated 12 exabytes. That's a lot of data. So the question is, are we only analyzing the tip of the iceberg. So unlike global warming, the icebergs are getting bigger. And they're getting bigger mostly underground because your CPUs are not getting faster and your data processing solutions are not getting faster. So maybe we need to think about something else because we don't want to be in this scenario because the Titanic can crash into this very easily. But this, they're likely to avoid. And there's a bear on there, which means maybe he scored. I don't see any food. I hope he doesn't starve. So, you know, we need to lift that iceberg up. And this is not a realistic iceberg because half of it is above. But, you know, we're not into iceberg realism. We're talking about data. So that was the problem. Now let's talk about what I'm going to talk about, really. So why GPUs? What are GPU databases, which is what we do? When are they good? And the future. So I'm sure you all know GPUs. You might not know that you know GPUs, but you know them. They're used for gaming. This is not a very new game, but you get the point. It's in everything. It's in your mobile phone. It's in embedded devices. It's in some of your cars. If you have like a collision detection system, you might have GPUs there. NVIDIA are really strong at self-driving cars. Tesla have a partnership with NVIDIA. Not just Tesla car. We'll get to that in a second. So what is a GPU? A GPU is a processor designed basically for display functions. It's designed to render video, render games, and basically show it on the screen. It's got a processor, which does most of the work, and it's got memory, just like a standard processor. But like I said, it's designed for graphics. It's designed to display things on your screen. For our purposes, I'm going to talk about Gpgpu, which is pretty much a GPU. I'm going to use the term interchangeably because Gpgpu is annoying to say. A Gpgpu is a processor, a graphics processor, that does not do display type activities. It does specialized calculations, like what we do in databases. You know, it's just generalizing it for non-graphics. That's pretty easy to say. AMD and NVIDIA both have their own processors. I will say this up front, SQream is mostly exclusively NVIDIA for now. We don't know what the future of that is. They're both advancing. AMD have ROCm, that's their CUDA alternative, if you've heard of CUDA, I'm sure you have. Then that's their alternative, and it's up and coming, and we hope to see it advance. So, let's talk core count for a second. Does anyone know how many cores this thing might have maximum? 18, 8, 16, 30, 24. Okay, I heard 30. 30 is close enough. The actual answer is 28. That's the maximum these things go. Intel Xeon goes up to 28. With hyper-threading, you might get 56. You might have 2 of these in a server. So that's 112 cores. That's not bad. 112 cores. Pretty impressive. And NVIDIA Tesla P100 from last year will have 3,584 cores. I remember that number correctly. I'm proud of myself. 3,584 cores. Now granted, these are not the same as Intel cores. They're much simpler. They don't have the same caching, branch prediction, all that stuff. But 3,584 cores is a lot. And you can do a lot with that amount of cores. Should I move over here? I think you guys are looking there, not here. So GPUs used to be a strange thing. They're no longer strange. You can find them pretty much everywhere. Many hardware manufacturers, Dell, HP, Cisco, they all manufacture solutions with NVIDIA cards. They're pretty much on the cloud everywhere. I'm going to move here, I think that's they're on the cloud everywhere. Azure, you know, Alibaba, Amazon, Bluemix, Google, they're everywhere. They're even on Oracle, right? I'm not going to say anything. So let's talk for a second about how GPU acceleration works. Because you can't just throw a GPU into the problem. You can't say, oh, I'll just stick a GPU and it'll make everything fast. You have 3,584 cores, great, let's run everything on that. It doesn't work that way. It's just not that simple. In reality, you have to take a bunch of operations that you can parallelize and offload them to the GPU. So you still have a bunch of CPU code. You still need the CPUs. But the GPU is sort of used like a math coprocessor from whoever remembers back in the day. So about 10% of our code at SQream is GPU-oriented code, stuff that is easily parallelized, and we push that over to the GPU, and everything else remains on the CPU. So, what are GPU databases? Now we get to the real interesting part. So a GPU database is either relational or non-relational. We like relational, we'll get to that in a second as well. That uses a GPU to perform some database operations. We're typically seeing GPU databases as being directed towards an environment that's been oversold on Hadoop for analytics. A lot of people think Hadoop was designed for analytics. It really sort of hasn't been designed for that. It's not too good at that. There have been a lot of products that have been aimed towards analytics on Hadoop. And we think they're not doing too good a job. Hadoop is excellent for what it's designed to do. Analytics, not so much. So GPU databases are also typically pretty fast. But they're not just disrupting, let's say, the in-memory database crowd, which is designed for fast analytics. They're also good at processing different types of data or processing a lot of data, like huge quantities. And that's really what we want to talk about. So why GPUs in big data? Really, it's about getting that big core count to do a lot of operations, to really punch through that huge amounts of data, perform these repetitive operations, and database operations like joins, group bys, order by, these kinds of database operations work pretty well on the GPU. We can also talk about it for cryptography, which is what the GIF was about, but we'll get to that in a second. So, database market. There have been a lot of new databases, and I know you're saying, why would you make another database? And the answer to that, pretty much talked about it. It's a pretty crazy idea. There have been a lot of in-memory databases because memory is cheap. And these are just a handful, and some of these are GPU databases. They're also in memory. I don't want to talk about them too much. But in-memory databases sort of struggle around that 2 terabyte range because hardware is not typically designed to do more than 2 terabytes. So what they do is they scale out. And when we're talking about scaling out these already pretty expensive hardware, we get to very, very expensive solutions. SAP HANA, for instance, which granted is one of the more expensive solutions, to handle 40 terabytes, it will cost you about $22 million for 4 years. And that's not my number. That's a number from a company that actually bought that, okay? So that's not even the list price. That is the actual cost. So that's a lot of money, especially for a small company. So, GPU databases. There's more than one type. There's the in-memory GPU database. MAPD and Kinetica are big in that realm. They're good for shaving that query down from let's say 1.5 seconds to 500 milliseconds, 400 milliseconds, and they're very good at what they do. Our type of GPU database, SQream, is more designed for big data. So we're not going to shave your query down from 1.5 seconds to 500 milliseconds. We're going to take it down from hours to 2 minutes. Okay, and that's where we see the future, and I'll talk about the future in a second. But I think that's important to say. We're not about the millisecond range. We don't care about that, personally. And we think that that's the future because if you remember, I showed you data is growing exponentially. You need something to handle that data. And in-memory is not going to be able to handle that without scaling out and becoming really, really expensive. So we say, don't buy the hardware, buy the results, okay? You don't need to explain what a GPU is to your boss, because your boss doesn't care, okay? He doesn't care what kind of chips are in the server. He cares about the results. And we think you should, really examine the database based on the results that it gives you, based on what it can give you from a business perspective. If it can give you faster queries, if it can give you access to more data, that's really where we see it shine. Because no data scientist has ever said, give me less data faster and I'll give you more accurate results. That's not a thing. Okay, well, I haven't heard of it. Maybe you haven't. I don't think it's very common. We think the more data you analyze, the better off you'll be, the more accurate your models will be. So I'm going to show you a few stories, specifically from our customers, but because that's what we know. So we actually have a big telecom out in Asia. And they were looking to do analytics on their customer base. They have 40 million customers, which is not a small amount of customers. It's pretty substantial. And they just did not have the ability to really get a holistic view of their entire network, see where their customers spend time, where they work, where they live, where are they Instagramming more. And they really wanted that ability. So they came to us and they said, help us do this. And we wanted to achieve also. And that's actually a live, not live, but that's a recorded dashboard from one of their solutions. And it's difficult to say, I don't understand the language, it's a very difficult language, but you can't mistake their face when they suddenly see this and they say, holy crap, you did this, you gave us this solution. I'm sorry for cursing, by the way. You gave us this solution, and they say, okay, click that, I want to see more, expand the time frame. I don't want to look at 5 days, I want to look at 10 days. I want to see where our people spend their time. I want to see what they're exposed to. Are they looking at our competitors' billboards? We want to know this stuff. And we gave them that ability. And that is interesting because we were up against a Greenplum database, which is not bad. It's a pretty good database. It's columnar. Is it okay? Can you see the numbers? So the ingest time was 20 minutes for SQream versus 300 minutes for the Greenplum, which was already pretty impressive. And the query time was also knocked down from 2 hours down to 10 minutes. And they didn't believe us. They went row by row, value by value to compare it because they didn't believe that this was actual data. And they had us run it on different dates and different numbers because they said, there's no way you weren't re-aggregating this because that's what we do on Greenplum. This is why it takes so long. And you were just running that on raw data? Yes?
Do you have any sense of the scale of the data we're looking at here? 40 million nodes in the sense of customers.
So this is 6 terabytes in this situation. I'll show that in a second because that's the important bit. The amount of hardware they needed to do this in 2 hours, run that report in 2 hours, was pretty big. But with SQream, we took one of their old boxes and we added an NVIDIA Tesla card. That was a $4,000 investment from their side on hardware. And 96 gigabytes of RAM. They would not budge on that. We wanted more, but they said, this is what we have, use it. And we were pretty happy with the results. They were pretty happy with the results. And I would say that's a win. So this is 6 terabytes of data. That's not really big. They are expanding the project. That was like the beginning of the project, just to show them how this works. And this was done in 4 days. So start to finish of this project was 4 days on site. I'm going to show you another one. This is against IBM Netezza, which is a pretty formidable opponent. It's very fast. It's also, as you know, extremely expensive. And we were doing something called an ACV calculation, which is a retail type of calculation that really looks at the entire retailer across the entire country. We can't name this company because they threatened us very severely if we did. And this is something that they ran. We did not run this ourselves. They ran this test. And they gave us these results. And we matched Netezza, which was very happy for us. It was a very happy moment. 24 terabytes of data, 300 billion rows joined with 8 separate tables. Tens and hundreds of millions of rows in the other auxiliary tables. They're too small to mention compared to 300 billion rows. And once again, it's sort of the same story. I think you're getting the point here. 8 Netezza servers compared to a single Dell box with iSCSI attached storage. And that's where we really see GPU databases shining. Because this was done on raw data. We didn't pre-aggregate, we didn't have to create manual indexes. The GPU is just really good for that. It helps us compress everything, it helps us tag metadata, it helps us do reverse lookups, inverse lookups to find out where not to look for the data. It helps us with the join, it helps us with the order by, with the group by, with the distinct. It helps across pretty much every SQL operation. And I think the cost of ownership here, once again, speaks for itself. It's a really, really big difference. One more thing, one more scenario, which we've actually done with a company out here in the US, which once again, no name for our own reasons. They were doing trillions of ad impressions. They're an ad tech, and they were trying to calculate bidding histograms. They're trying to get the most out of the data that they have. And they started out with something like 85 terabytes, and they said, show us that you can do this on 85 terabytes. And we started out with a single server, and they were very happy with that, so they expanded that. And now we have 8 Tesla GPUs working to really get that workload ready. And that's compared to their HBase / Phoenix solution. So they were used to querying HBase with Phoenix. It would take them about 5 hours to get the results, which is, it's a lot of time. And our solution was able to do that in 5, which is why they expanded. And that's pretty cool, I think. Because that's a lot of data. And this should advance. And it doesn't. All right, let's see it in action real quick, shall we? So I'm showing Tableau because a database, when you look at it, it's like, my colleague Jill says, it's like opening the tap in your house, opening the faucet. You see water come out, you're like, okay, it's a database. I get it. It does calculations. So we're actually using live mode for Tableau here. And live mode is interesting because it doesn't let Tableau do anything. It pushes all of the operations down into the database. So everything we do here sends a query down to SQreamDB, one or more depending on the situation. And SQreamDB does that in the background. So what you saw here was a 4-table join on a dataset that is 33.6 billion records, which is not that big when you think about it. The reason it's not that big is because this is a demo and we wanted to run, within milliseconds/seconds, because you're not going to wait like that publisher company did. You're not going to wait 5 minutes for a result. So SQreamDB basically takes all these queries from Tableau and runs them in the background. And this is raw data. So the second the data comes in, because it's tagged, because it's compressed, and all the GPU databases do this, right? They compress everything because that is an expensive thing to do, copying data to the GPU and back. That's an expensive operation. So you want to compress everything down as much as you can. And this database, these databases really allow you to access more data than ever before. You're not just looking at a billion records. You're looking at 300 billion records. In this case, 33, but 300, 500, 900 billion records pretty easily. And that allows you really to, for the first time, and this is not doable with any other database, not at this scale, really deep dive into your data, ad hoc query everything, look at, ask whatever you wanted, because until this time, you sort of had to think, okay, am I going to anger my DBA if I ask him to add another index to that column? You don't need to do that here, not with any GPU databases. We all avoid indexing, and that's pretty cool, I think. So one more thing, and this is a genome scenario that we have. This is a little bit different. It's not our classic use case for Scream, but we actually had a bioinformatician in our company. We still do. She developed this very interesting way of handling genomic data in SQL, in a relational database. And we sold the solution to a big research facility in Israel. And they were used to doing, let's say, a handful of people. They were used to comparing a handful of people from like someone's ethnicity to find if there are similar anomalies in their genome to understand, is this person more likely to get a specific illness? It was mostly done for cancer, but other illnesses as well. And they were used to doing that in about 2 months. So they would compare 6, 7 people to one person in about 2 months. That's a lot of time to wait. And the person waiting, they know they gave their DNA, they're waiting to know if they have some genetic condition. That's a long time to wait. And with SQreamDB, they're actually, this is one of our smallest installations from a GPU perspective. It's only 2 GPUs, because they only have 2 people running queries against the system. But this is our largest installation in terms of data. This is a 1 petabyte solution that we installed for them. And they're able to now analyze hundreds of people within hours. Sorry, not minutes, hours. So, I mean, hours is a long time, but it's nowhere near 2 months to wait. Imagine you're going in, you give your DNA, they run this analysis, and within 2 hours you have your result. And we're not making a lot of money off this thing specifically, but we're okay with that because this has the potential to change people's lives. And this could affect people that you know. So that's why we're doing this, even we're sort of losing money on this one. Chanel might say that server racks are fashionable. They had this thing last year. Our customers, they don't really like server racks. And we say, be efficient with your hardware. If you can take a single server, stick a GPU inside, or a couple of GPUs, or 4 GPUs, depending on the chassis, and you can do so much more with that. And a typical SQreamDB installation with 2 GPUs in one of these boxes will be able to handle about 40 terabytes. That's efficiency. That means you can do so much more with so much less. And that's really, everyone's talking do more with less. This is it. This is where things get interesting. And you're thinking, okay, that's a bit scary. We don't want to change your database. But it's compatible with everything you already have, right? It's, in the end, it's standard hardware. The only hardware requirement is a GPU, and it has for our case, it has to be an NVIDIA GPU. That's not true for all GPU databases, but we just found that CUDA is the most advanced platform right now, so we're strictly on NVIDIA for now. And you can connect any storage to it. As long as it's mountable in Linux, for us, we can use it. And scale out is just as easy. Just add more compute nodes as your workloads get more elaborate and more complicated. So let's talk about the future, because until now I talked about the present. So the future, I don't want to say, change your database right now, because that's a scary thing. That's sort of why we say let's look at it together. That's why we're offering this thing. Let's look at it together. Let's find out if this is the right thing for you. It might not be. It's not good for everyone. But changing changing databases is a scary thing. It's right there in the scary zone. It's not cold fusion, right? It's not something completely out of field. I have no idea where this landed upon me. But it's not really incremental either. It's a little bit different, but in the end, it's SQL. You know SQL. It connects with the standard stuff, JDBC, ODBC, .NET. You know that as well. It connects to all your standard stuff, all your BI tools. No big, right? And we think this has the power to innovate your entire data pipeline, because you will no longer be cutting down on your data. I said earlier, no data scientist has ever said, give me less data. This is your opportunity to give them more data. And the way we see it is, a GPU database will be good for some things. It's not going to be good for everything. You will still have your Mongo, you might have your document store, you will still have your transactional databases. That's fine. We're not going to replace everything. But we think there's a place for that, specifically for companies who need more data. Because these databases that are able to scale and are able to handle more data will be the ones who end up being relevant. And the ones who are stuck in the 1-2 terabyte range, they're going to end up being less relevant for a lot of use cases. Not for everything, there's still going to be a place for them, but they're going to be a little bit less relevant. The rising GPU offering in the cloud is a big opportunity for anyone who doesn't want to pay upfront for the GPUs. You already have pretty much every cloud provider, as I mentioned before, has GPU instances. You can just go on, pay for, on demand, a couple of dollars per hour, and get a pretty strong GPU instance. You can also pay for spot. It's a little bit more economic if that's your thing. These per hour are pretty expensive. But they will allow adoption by so many more people who can just spin up an instance, try it out. It's good. They continue it. If it's not good, you just shut it down, and you don't even have to buy your own GPU. From a hardware perspective, we are seeing very interesting things, both from NVIDIA and from AMD. They're really advancing their stack. AMD with ROCm have come a really long way from just OpenCL / whatever they had to ROCm, which is very, very close to CUDA in terms of performance. And NVIDIA have really advanced their CUDA platform, and it's really easy, relatively easy, let's put it that way, to write good performing GPU code. It's not as difficult as it was in the past. I'm not saying anyone should do it. It still requires some work, but it's a lot easier today. The faster the GPU gets, the faster that we get, and not just us, MapD, Kinetica, the others, we will get faster as the GPUs get faster. And it's not just the GPUs, it's the PCI Express, with PCI Express 5.0 expected to be very fast. And NVIDIA already has HBM2 memory in their GPUs, which is very, very fast. It's got pretty intense bandwidth. And it's not just NVIDIA. Intel partnered with AMD. I think this is from last week. They partnered with AMD to create a single chip that is both CPU and GPU together. And that's going to be pretty interesting. We're sort of waiting to see how that plays out before we jump on that bandwagon. But that's supposed to be pretty interesting. And that's going to make everything fly. Reminder again, we will offer consulting to anyone who finds this interesting. And I want to finish on this slide again, mostly because I like the monkey GIF. But also these are pretty good points. Your boss doesn't care about the chips. You don't need to sell GPUs to your boss. You need to sell the solution. You need to tell them, or if you're the boss, then you tell yourself, right? But if your boss cares about this, you need to tell them what a GPU database can do. Not, the GPU can be really fast, because no one cares about that. And you should evaluate it based on what they do for you, not what they do for anyone else. You need to evaluate it for yourself. see if it's good for you, and only then keep going. Don't buy into these technologies before you try them out. I think that's it from my perspective. I'm open to questions. Let's start here. Yeah.
That use case that you came up with for Tableau.
Yeah.
Basically, they were just doing the join on your GPU for the database.
Yeah. So because we ran in live mode, all the operations were not done by Tableau. Tableau was used strictly for the visualization. Everything is offloaded into SQream through the ODBC connector. You get for that dashboard, there were 8 separate sheets, and each sheet generates its own SQL query, which is fired into SQream. And that specific server has 4 GPUs and 128 gigabytes of RAM. Just as a,
Sure.
if that's interesting.
Yeah.
Yeah. I don't know how to compare that to Google Bigtable. It's a different product. I don't know how to answer that. We've not tested against Bigtable specifically. We typically our scenarios go. We enter a specific customer. They have a problem to solve. We help them. Either they end up going with us or not, depending on what their future looks like. But we evaluate based on customer scenarios. We don't just go and generate our own data and say, it's faster in this TPCH scenario, because that tends to be a little bit misleading. That's what we found. I'm sorry I can't answer that any further. Yeah.
Yeah. Can you give us a more details as to what database dataset is very good for your system? And I want conversely, what is bad to use in your system?
Okay. So the best type of stuff that we deal with. So we're a columnar database. So anything that fits in a columnar database would be good, as long as it's mostly numerical and, let's say, relatively short strings. So if you're analyzing blobs, whatever, not the ideal solution. If you have images in your database, you want to do some stuff on basics, not our strong suit. We're good at numerical, and we're good at relatively short string operations.
Does it matter whether it's a double position or single position data? I mean, it doesn't matter because the double position take more bandwidth or something.
Yeah, it's just you have the amount of items that you can push into a GPU in a certain clock, but it doesn't matter for us in terms of the operation.
What's bad to use your system?
I'm sorry?
What database is not good to use in this system?
Long text, basically. Long text or binary operations, not the ideal situation.
Before we take the next question, I want to remind everyone we are giving away this drone in a few minutes from now, actually. If you have not already put your business card into the bowl, what this guy has been holding very patiently for a long time, please come up here and put it in. The bowl is going to sit here on this chair. Put your business card in there. If you don't have a card, you can write on anything as long as it contains your full business card information, including contact info. Put it in their card. We'll give that drone away in a few minutes, and let's take the next question.
I'm going to go like this, if that's okay.
Oh, I was just following up.
Alternate.
Okay, following up. Okay, sorry. I'll alternate. That's a good idea.
Again, this is towards mechanical concepts. Apart from like equi joins and low cardinality, columnar searches, how do you work with these, like trying to do an as of join, where you're trying to find the first one that's just shorter, that is less than this or something?
I don't think we have a specific solution for that just yet. We're a small company. We're just over 40 people. There's a limit to how much we can develop in one go. We were really, for the first 5 years of the company, we were focused on building something that we weren't embarrassed to show our faces with. We're building it as we go along, and it's typically based on our customer demands. So if we talk to someone and they say, we would really like this feature, we would develop it for them, but we wouldn't go ahead and do it. So that's something that's a little bit different.
Every SQL data is bad.
Yeah, we don't. I've not heard that from a customer yet. If that comes up, I'm sure our architect will find something to do with that. He's pretty good at that. Nothing just yet. So alternating. So, yeah.
Tableau actually issues multiple queries at the same time.
Correct.
So is that actually, without turning that off, because you can actually turn that off so that it's like
No, it's multiple queries.
So,
it fires off multiple queries. Because we have several GPUs, we can answer more than one question at the same time. and they run simultaneously.
Is there a limit on the number of queries you can run at the same time?
We typically like around 1.5 queries per GPU simultaneously. For convenience sake, we can split that up in several ways. Yes.
Two questions which I believe are closely related. When you implemented general SQL queries, you're looking at joins with nested. I mean, it can be complicated or not so complicated. You're kind of evolving like optimize it according to physics. But there must be some queries you cannot just leave one pass on the GPUs. You have to go to sort of a pipeline of operations. If that's the case, I was wondering the channel example, okay? Because I was surprised. It's a small data relative to the other signal. But still, that data won't fit, and the two GPUs will match.
Correct.
So you need to move stuff as you do that pipeline back and forth from some main memory to the GPU back and forth. I'm surprised how can you really do that fast.
That's our trade secret, actually.
Okay.
So it's not even patented. It's a trade secret.
It's a trade secret.
I can't go into that. We have a lot of layers. We have a lot of things going on. Most of our really interesting things are actually in the compiler, or in the SQL compiler.
Okay, so it's a lot of compiler.
It is a lot of compiler work. We do something in the vicinity of 300 to 400 rewrites to a query where we convert it to an equivalent form that would run better on the GPU for several layers. It's pretty complicated. Yeah,
But it's still impressive. I mean, it's like, wow. Okay.
Yeah.
And that's just a small example. Because the big ones, like, never really wrap my mind around. That one was kind of magical.
And you can imagine how difficult it is to test as well. Right?
Yeah.
You're testing huge data sets. You're like, how do I generate this in-house?
I was thinking about generating test cases. The Japanese company, whatever, say, okay, looks like it's only investigated.
It's difficult.
The results are accurate.
Yeah, it's not easy. If it was easy, everyone would do it. Anything from you? Yeah.
I'm a little confused here because I get the impression that most of this exciting, interesting material is not for 99% of us in this room, perhaps even less. But I'm sure that there's a big audience out there, and an audience who can use or consume or end user who could use it. Do you see a point where this is obviously for desktop type of equipment that eventually we can get to as users?
Actually, yes. So we do have an implementation on ARM processors. So NVIDIA have something called a Jetson, which is ARM 64 based with a GPU on top. We actually do run on that. So I don't have any benchmark to show on that just yet, but we do run on that.
Eventually it goes down to 3-5 years, 3 years from now.
That's part of our vision. We do want to get down to that so that we can say we're analyzing data on the endpoint and we're only sending back the analyzed data instead of sending back everything. Don't send raw data, do the analysis at the endpoint and only send back the analyzed.
Many other things can be used to be benefited, including health information, that kind of things. If you have
autonomous cars, airplanes, anything you really want to collect information and you don't have that space. 100%. That's part of our vision. I didn't put it in the future because we don't know if it's the future or not, but
it sounds like the future.
Maybe we'll see.
You know, the big thing about is, as Arnon said, if you're using, let's say, even you're getting really good and you're using 10 terabytes of data, maybe you're Redshift, an AWS, or between Hadoop and Spark, and you have 100 terabytes, like you said, small companies can collect that. You're now analyzing 10% of your data. Your predictive and prescriptive analytics should be pretty good. But now, many companies have petabyte data. If you got really good and you invested a lot more money and you got to 20 terabytes, you're now analyzing 2% of your data. And it's probably, maybe you're okay, maybe you're not, but you're not getting better. So when we see companies saying we're going to be in exabytes in a couple of years, even if you just go to 10 petabytes of data and increase and say, we'll double again, we'll get to 40 terabytes, you're now down to less than 10% of your data. And you think your analytics are getting better, but every data scientist will tell you it is not. We're going in the wrong direction. So we're looking to change that direction and say, American businesses, if you want to get ahead, then if you can do better predictive and prescriptive analytics for causation and correlation, you're going to come up with better insights than your competitors. Just like what Amazon did to the retail industry by being data-oriented. That's something to think about.
Yes.
Yeah. So you said that this is a lead room, cloud services. So
Yeah.
if I have a use case, or if I'm participating in a foundation which is a use case more than 10 terabytes, I can found it on AWS and everything. I have a use case, I want to show that how fast it is on user basis. Also, the other thing is that how this is useful for real time, like streaming. And some say that there are some applications which will do the analytics at that point rather than storing the data. Doing the analytics once the real time the data is coming and then storing the aggregated data. So how does this work in real time analytics? And how can I find this thing on AWS if I want to pick a use case or competition where?
So first question is, how do you find it on AWS and use it? Talk to Crystal, you talk to Matt, they'll take care of you.
It's not in the public marketplace just yet, because we still like to control that, make sure that you're getting a good experience. So we like to make sure that you know and understand what this is good for. Because we don't want you to start using it and say, this is not what I was looking for, why I spend time on this is terrible. So we like to help in facilitate that process. For this moment exactly, this is going on the marketplace very soon, probably within a month.
How about the real time? You think rather than stored data, if I'm getting something like IoT or streaming, I want to do analytics at that point of time and store the analyzed data.
So that might not be in our, in our core competence. We're good at taking large amounts of data, analyzing them. If you're talking about getting this data in and analyzing it as it comes in, you might be better off with something else.
Now, if you have, though, we have a customer who's got a large database, and they are in that ad tech play, they care about 30 days. So if I bring in 50 to 90 terabytes today, and that's date 32, then I'm going to roll off the 50 to 90 terabytes. As soon as that gets in, it's available for query. If you add another column to your database, you can still work, and it'll reverse that in, and then it's available to be part of the query. So speed to insight on very large data sets and being cost efficient is the value proposition.
Yeah.
You mentioned an IBM that's using use case up there. How do you do on a 10 or 20 terabyte aggregate the table scan? And however your answer is, why would you be whatever your answer is?
For a full table scan, we will be faster than Netezza, and the reason for that is we do a lot of compression already, and we have a very interesting mechanism of handling how we copy data back and forth, which is, like I said, a trade secret. But the compression really plays a really big part in that, and the reason for that is the GPU is really good at compressing and decompressing. It's essentially a free operation for us. So we don't care if we compress everything as it comes in, and we tag it as it comes in. And so this is not true for a full table scan, but if you're only looking at a specific part, our negative index will know, how to pinpoint that exact data.
Are you saying you actually process data compressed, or do you uncompressed?
Depends on the query. Some stuff we do operate on compressed data. It's going to depend on the query. Yeah.
So once you do your query, your table query, it doesn't matter how you do predictive analytics. If you want to use sparse analytics.
Yeah, you just, you pull the data out, you query it, pull it out, and you do whatever you want with it. It's just a database, right? In the end, to the end user, it'll look like just a standard database. They don't need to know there's a GPU behind it. They don't need to know how much RAM there's in the machine, how many cores. They don't care. They care about writing the query, running it, and getting the results. That's true for this situation as well.
Large companies who invested in the Teradata and the teasers and so forth, and they start to move users off into a in-memory and Hadoop combination, and the first thing they say is, what happened to my performance? Why can't I get it like I did then? We spent $10 million on that box, spending a lot less here. It's kind of the future. So this is a way to bring that kind of performance and get more scale.
Are you guys going to sit essentially as a software play on top of GPU performance increases, or are you looking towards optimizations at a system level, for instance, for block I/O? In other words, if you're in a big database appliance, a persistent database appliance, you may look towards optimizations where you're really thinking about I/O as well as computation. Or you could use a commoditized I/O scheme, like whatever the operating system or the file system or whatever it is. Or you could look towards systems that parallelize I/O, for example, in scenarios like that. So are you guys in that business, or are you just going to sit on top of kernel cores and what do you see?
Right now, it's a lot based on the operating system. We do have some custom stuff, but we're a software company. We don't care for the hardware. We don't want to do like direct RDMA from the kernel. We're not really in that field. We're software, and whatever we can get from the operating system, and working cleverly with the operating system and understanding the limitations and the opportunities that are to be had from this, we will use the operating system to its full extent. That being said, we're not completely oblivious to all these new improvements that can be done with special hardware and special calls and doing custom stuff. We're looking into that. For the most part, it's mostly on top of the operating system for now.
Just a follow-up question. Do most of your use cases sit on top of solid state or a spinning disk?
It's about half and half, actually. It depends on the situation and what the customer is trying to achieve. If they're looking to cut costs, we can work on top of spinning disk. We don't care. If they're trying to get more performance, we will advise an SSD, but the customer is the one who buys the hardware essentially. We recommend, they buy it.
You seeing a derivative of any sort of sign up a derivative in terms of what I take for SSD is? Rate of growth.
I'm not sure how to answer that question.
Okay.
Yeah.
Are you guys looking to embed your analytics as part of your database?
Yes, we are.
Okay.
There's nothing in the database right now that can allow you to do like
machine
learning inside.
Right, like we have R inside of SQL now, and that's kind of like the trend.
Yeah, Microsoft has so many resources to put on embedding R.
Yeah,
that's a bit of a.
But I was just wondering because it sounds like you would have an advantage in that space.
Yeah, we're looking into it. We have some interesting things coming up. Nothing public just yet.
Okay.
Nothing I can talk about.
All right, I got it.
Currently, you can use Spark for the
You're waiting upon the signatures.
No, that's where I see you can differentiate.
To do the next sentence.
Pretty much.
Right there.
We're waiting to see how that.
You don't have to move to that.
But I can use it inside R or Python with some libraries or something.
They're just connecting, right?
Yeah, just through a standard connector. JDBC. I would recommend JDBC specifically for R, but just a little bit of lower overhead for that.
Got a question then?
Yeah.
Do you prefer a few fat nodes, or do you prefer more thin nodes? What's your preference?
Depends on
a lot of GPUs on a node, or you can go to a 16 XL on AWS, for example.
Yeah.
Or do you prefer to have double, triple, quadruple thinner node? What's your preference, and why is that?
It's going to depend on the situation for the customer. If they have a whole lot of users querying the system at the same time, we might go for a higher GPU count. If they're just interested in getting more data and they only have a handful of users, we will go for thinner nodes and just better storage.
Does memory matter?
It does. We will use whatever the system will have to offer. I mentioned we work on top of the operating system. Everything we can gather from the system, we will use. There are configurations, right? You can set it, but by default, we will use whatever we can get. The more RAM you have, the better. But there's no specific requirement that says we need 1 terabyte of RAM. That's not a thing for us.
We have time for 1 or 2 more questions, but I just want, after those 2 questions, we're going to give away a drone. So if you did not have a chance to put your business card in here or something else, like this guy cut out half a plate, and a business card out of it. If you have not done that yet, put it in now so you have a chance to win this awesome drone. Last 1 or 2 questions. You had your hand up? Someone in that region? You did. Okay.
Have you tried running on really big iron?
Like what?
Big supercomputer.
No. We don't have the resources to to do that.
Have you considered talking to one of the big defensive science shops that would maybe sit on top of it as a test run?
We're
something really big.
We're in talks with some very interesting companies doing, big and small companies doing very interesting things with expensive hardware. That's not typically what we like to do because we like to keep costs down. We like to be accessible. We want it to be used by anyone. So we're not at the point where we're writing like specific code to handle like on a Cray computer. Are they still a thing?
Yeah.
So we're not writing specific code to be handled on supercomputers because we would like to stay accessible. That's part of our value, I think. Having said that, given the opportunities, and there are a few in the pipeline, we are open to testing, and we've actually recently ported to IBM in Seattle. That's not like supercomputer, but it's pretty fast. It's pretty impressive hardware. It's got NVLink, which is like the NVIDIA technology that allows not just fast inter-GPU communication, but also between the CPU and the GPU. So we're already seeing about a 1.7x improvement with IBM Minsky compared to standard x86.
Power 9.
Power 9 is in the, we've not had access to that machine yet, but once you port to Power 8, Power 9 is just...
These guys hand up, that's the last question.
Can I make use of this GPU in-memory application instead of directly storage?
I'm sorry, I didn't understand.
Is that computable? For example, use of some in-memory application, which means when you will save, it will not save in the disk, it will temporarily save in the memory and reduce some computation.
So it's another one of those little bit trade secret areas. We use the RAM, we use the cache, we use whatever we can get from the system. So some stuff might stay in the RAM, some stuff might stay in the cache, and it will be faster to operate on. But having said that, every piece of data that comes in gets stored almost immediately. It's easy to do because it's a columnar database. You just append things to the end in most situations. So it's easy to do that. And the in-memory situation is a little bit different because they have everything in the memory all the time. And we don't do that. We do offload data to disk and we read it as we need it. Does that answer your question? Okay.
Okay, Arnon, Ami, and Joel are here for one-on-one questions right after the raffle. If you want to talk to Ami, you got to kind of do it quick because he's got an airplane to catch. But they will be here for one-on-one questions. I want to give a great big round of applause for Ami and Arnon. Now let's give away a drone. Can I ask you just mix it all up? Can I ask you look that way? And then reach in, pull one out. They're really not looking. There you go. Now read what it says. Read the name. Maybe it's the other side? Wait. There's no name on there. I said we gotta make a business card. Throw it back in, reach in, grab a different one. I say gotta make it like a business card. Alright, read it out.
Brenda, Alex,
Alex Blaine.